All right, last problem. Page 17, example 4. Manufacturers make widgets and gadgets. There's at least 500 widgets and 700 gadgets are needed to make minimum daily demands. The machinery can produce no more than 1,200 widgets, 1,400 gadgets per day. The combined number of widgets and gadgets that the packaging department can handle is 2,300 per day. If the company sells both widgets and gadgets for $1.59 each, how many of each item should be produced to maximize profit? So I could say X is the number of widgets and Y is the number of gadgets. So the profit function is they sell both of them for $1.59 each, 159X plus 159Y. So we need to now come up with our inequalities. There's at least 500 widgets, so X must be greater than or equal to 500. There's at least 700 gadgets. Y is greater than 700. And if the machinery can produce no more than 1,200 widgets and 1,400 gadgets, then I'm going to actually change these. So the number of widgets is between 500 and 1,200. I'll write that as a double inequality. And the number of gadgets, if it's bigger than 700 but no more than 1,400, I could write it like this. And then combined number of widgets and gadgets is 2,300. So I'm going to write it like this. So these are my inequalities. So even for the last one, the intercepts are 0, 2,300, and 2,300 comma 0. I'm going to go by 200s. So again, there's no exact science for figuring out the scale. I would find the intercepts, and based on the intercepts, that should help you out to figure out a good scale. So I'm going to graph the last one first, just by plotting the intercepts 0, 2,300, and 2,300, 0. So we know it's in here. X is between 500 and 1,200. So here's 500, and here's 1,200. So it's in between these two. And then Y is between 7 and 1,400. So here's 700, and here's 1,400. So here's a region. In red, I'll shade. So what we need to do is we need to find all of these vertices. And once we find these, we're going to plug into this function. This is 400 comma 700. Or I'm sorry, 500, 700. This is 1,200, 700. This one is 500 comma 1,400. The next one, this is 1,400. And if you plug into this equation, X is 900. And then the last one, this is on 1,200. And 1,200 plus 1,100 is 2,300. So we need to plug all of these into this profit function. And if we want to maximize the profit, we just want to know which value is the biggest. So we have 500, 700, 500, 1,400, 900, comma 1,400, 1,200 and 1,100, and then 1,200 and 700. So it's a lot of plugging in. These are applied problems. But if you plug them all in, you could find the maximum profit. So this is all the work that you would do. And then after, we're going to just plug in and see what we get. This is 1,100. And last one, 1,200 and 700. So if you plug in values that I got for the first one, I got 1908, 3021, 3657, 3657 again, and then 3021. So there's a tie. So it's either 900 widgets and 1400 gadgets to maximize profit, or we could say 1200 widgets and 1100 gadgets. So these are all the same way. The key for these is starting the problem off, defining the variables, writing the profit function, and then writing your inequalities. That'll get you going. If you then graph them and plug in all the vertices from the polygonal convex set, that's the way to get these right. So these are the notes from page 17, last page from chapter 2.